and welcome to this lecture. We are in module 10, lecture number 5. In this lecture we will discuss about intrinsic charge calculation in quasi-static operation. We will introduce how to incorporate the intrinsic charges with respect to terminal voltages for strong inversion and moderate inversion. So, these are the learning outcomes of this lecture, which helps you to understand the quasi-static operation when you are going to relate the charges which is available in the transistor with respect to time varying voltages. Let us do a quick recap. In previous lecture we were discussing about the quasi-static operation, mentioning that when the terminal voltages will vary very small, right, it means Vg, the variation of this terminal voltage will be very small, then we can consider the quasi-static operation and the DC operation as similar. However, though the charges and voltage relation will be applicable same as DC analysis, however, the terminal current cannot be captured by the DC analysis. We have taken an example that in the quasi-static operation, that Ig, the gate current, is due to change of gate voltage per time, which was not the case when we were discussing about the DC analysis. We started our analysis with considering a fictitious MOSFET and remove the source and drain side, and we said that all the terminals is associated with the terminal voltage with some reference. Then we said that the total charges in the channel can be calculated as Qi is equals to W into 0 to L Qi dash dx, where Qi dash is charge per unit area. So, this is inversion charge per unit area, and that is what we are per unit area, and that is what we are multiplying with the area to calculate the total charge. Then we said that we can represent these charge in terms of some functions of terminal voltages. We can use the same analogy for the quasi-static, meaning we can simply say this kind of charges like gate charge can be represented as some function of Fg with terminal voltages as Vg, Vd, Vs and Vb, where the small notation is used for time varying signals. So, Qg, a time varying gate charge, right, it can be represented in terms of terminal voltages. However, the current will not follow the same rule which we have shown in DC analysis. Further, we said that when you are going for a quasi-static analysis in source and drain region, further we have said that when we are going for quasi-static operation of MOSFET, then the rate of change of gate charge causes the rate of change of inversion charge. It means if you increase the gate voltage very slowly, then the rate of change of inversion charge should change, meaning the inversion charge in the channel will change. Now, how this inversion charge will change? If you increase the gate voltage, then the inversion charge should increase by a small amount. Now, to increase this charge, there is a fictitious charge coming from the outside in the source. At the same time, the exit of the charge at the drain will be lesser, and hence we define some additional currents which we called it as ISA and IDA. These are the additional currents, or we call it as charging currents. We showed using some expressions that IDT can be given as IT plus IDAT and IST can be given as minus IT plus ISAT. There we have also discussed that IDA plus ISA is nothing but delta Qi divided by delta T, where corresponding to these extra current we defined some fictitious charges associated with it. We said that this is nothing but dQd divided by dt plus dQs divided by dt is equals to dQi divided by dt. Now, let us see how can we calculate these terminal charge and voltage relation such that we can use in our final expression to calculate the current as rate of change of charge per rate of change of voltage and rate of change of voltage per So, we are going to form a relation between charge and voltage. Now, in general, when we are talking about DC analysis, then these charges are related in some closed form equations. We have already derived the equations in terms of Q and surface potential, as well as Q and some terminal voltages, whether it is VCB, VDB and VSB. So, we are trying to preserve the previous analysis which we have done for DC analysis in our quasi-static operation. Let us see for strong inversion case. We are considering that the gate voltage is enough that you are in strong inversion. So, this is your fictitious MOSFET with the terminal drain, source and the gate and also the body here, and you are applying the voltage from the gate in such a way that you are in strong inversion. Now, we know that in strong inversion the current is basically given as ID is equals to mu into W into minus of Qi dash into dVCB divided by dx. Here the current is related with dx. Dx is nothing but along the x how the current changes, right. So, this is 0, this is L. Now, we have also derived a equation where my charge is related with distance 0 to L Qi dash dx into W, right. But I do not have a closed form equation which relates how the charge varies with the distance. So, I need to change this variable. So, to change this variable I can rewrite this equation as dx is equals to mu into W minus of Qi dash divided by I ds into dVCB. The variable here we are considering that IDSN, it means strong inversion non saturation case. Now, obviously the limit of x is 0 to L. Similarly, the limit of VCB is VSB to VDB. These all things we have already discussed when we were doing DC analysis. So, using this variable of dx, we can simply find out the charges what we have defined in previous lecture. That is, if I want to calculate the total inversion charge, I can simply calculate as W into 0 to L into Qi dash dx. So, this variable we are changing in terms of VCB. So, I can rewrite this dx as mu into W with a negative sign into Qi dash divided by IDSN, and this Qi dash is also coming here. So, it will become Qi dash square dVCB. Now, the integration will be done between VSB to VDB. That is what is the expression written here. That is, Qi can be calculated as mu into W square divided by IDSN into integration of inversion charge square between VSB to VDB with a variable as VCB. Similarly, following all those expression like for QB dash, what happens is W into 0 to L QB dash dx. If you keep dx and change by this function, you will get W into 0 to L QB dash into Qi dash with a negative sign, and this constant will come out as mu into W divided by IDSN dVCB, and now the limit will be VDB to VSB. So, that is what the closed form equation of the charge with respect to voltage is coming like this for quasi-static analysis, right. Here Qg is dependent on Qg and Qi. Total Qg is nothing but this is the same one that we just rearrange the constants, taken these constant out, and Qg can be written as this. Similarly, Qi can be written as this and Qb can be written as this. Now, when you are going to calculate the charge Qd and Qs, you require x, because you remember that Qd charge was calculated as W into 0 to L qi dash into some weight we assigned at the drain side and at the source side. So, at the drain side the weight was x divided by L into dx. We just showed how to replace dx. So, dx can be replaced as minus w into mu divided by IDSN into dVCB, where the limit of dVCB is nothing but what? VSB to VDB. Now, how you replace this x? For that, let us consider this is your channel starting point and this is your channel ending point. We have done this analysis when we were relating the position with potential. So, let us consider at any arbitrary point x, you want to relate the distance with potential. So, how we can do that? We consider that this point is arbitrary drain. At that moment the voltage is VCB, right, and the distance is x. So, we can rewrite this equation and integrate this equation from 0 to some arbitrary x. So, when you integrate this equation, you will get x at the left hand side, and at the right hand side you will come up minus w into mu. So, I am doing integration of this, right, divided by IDSN into, you need to put limit. The limit at the x is equals to 0 is nothing but what? VSB, and now you are calculating at some arbitrary x. At that moment the limit will be what? VCB. So, that is what the limit will be, VSB to VCB, and you need to integrate as dqi dash, here qi dash will come, and sum with arbitrary variable or dummy variable du Cb. If you solve this equation, this will give you the value of x. Now, you put back this integration back to this integration to calculate overall Qd. Similarly, to calculate Qs, you need to assign the weight of 1 minus x by L. Here the x can be put by this equation, right, x can be replaced by this equation where you need to solve. Here x can be replaced by this equation, you will solve this equation, put the value of x and solve for Qs. So, now this, when strong inversion non-saturation model converts into strong inversion saturation model, then you need to replace the VDB voltage by Vp. That is what we have already done, that a general form of inversion charge when VDB is less than pinch off voltage is can be given as VGB, VSB and VDB, right. But when you move or when the drain voltage is increased beyond the pinch off voltage, then this function is replaced by Vp. Now, let us see all this analysis for a general case of source reference simplified charge model. In the sense, let us take an example to understand how we can calculate the overall charge by using the previous approach what we discussed related to quasi-static operation. To do so, let me give you again the recap of the basic equations what we have derived as IDS is equals to IDS dash into 1 minus eta square, where eta was defined as 1 minus VDS divided by VDS dash, and VDS dash was defined by the slope of IDVD characteristic and keeping it 0, that value was VGS minus VT divided by alpha. Again, the assumption here is we are considering the long and wide channel MOSFETs, we are not considering the short channel effects and the velocity saturation, right. So, to do so, we can use these basic equations and a constant eta to move further to calculate the Qi dash for strong inversion case. Now, to move further again, we need to know what is Qb dash and Qi dash in case of source reference model. So, if I write for Qb dash, this will give me Cox dash into gamma into root psi SE plus gamma divided by 2 times of psi SE into psi S minus psi SE. That is what we have discussed when we were discussing about the expansion point or the linearization of the bulk charge. At that moment we said that if we want to consider for source reference, this expansion point is nothing but what? Psi s 0. So, I can rewrite this equation as Cox dash into gamma psi naught plus this factor is can be replaced as what? Alpha minus 1 and psi s minus psi s 0. As we are considering the case of strong inversion, the surface potential can be replaced as phi naught plus VCB. This surface potential is what? The potential at arbitrary point x, that is what we just derived. Arbitrary point x, what is the surface potential? It is nothing but phi naught plus VCB, right. Similarly, the surface potential psi s 0 near the source is can be given by phi naught plus VSB. So, if we replace these values, we will get psi naught Cox dash gamma square root of phi naught plus VSB plus alpha minus 1 into phi naught plus VCB minus phi naught minus VSB, where this will get cancelled and ultimately you will left with this equation. Similarly, you can get what is the expression for Qi dash. We know that Qi dash can be written as minus Cox dash VGB minus V flat band voltage minus psi s minus QB dash. So, when you put again psi s is equals to phi naught plus VCB and put the values of this QB, solve this equation, you will get minus Cox dash into VGS minus VT minus alpha times of VCB minus VSB. When you solve this equation, you will encounter a quantity as V flat band voltage plus phi naught plus VSB square root into gamma. That quantity is nothing but what? Threshold voltage, which is replaced here. You will get another quantity as VGB minus VSB. So, VGB minus VSB is replaced as VGS. So, ultimately we do have a closed form equation for Qi and QB. Now, if we wish to calculate the total charge, we can use this expression, that is what we had derived earlier, right. So, to use this equation, I can calculate Qi is equals to minus mu into W square divided by I dsn integration VSB to VDB into Qi square. So, here I am using this formula. Qi square means will give you Cox dash square into VGB or VGS. Instead of writing VGB minus VSB, we are writing VGS. So, this will become VGS minus VT minus alpha into VCB minus VSB whole square dVCB. For sake of simplicity, I am assuming VGS minus VT as A and VCB minus VSB as let us say U. We need to integrate with respect to VCB. So, we need to change the variable dVCB is equals to du. Accordingly, the limit will be what? If you put VSB, the limit will be 0. If you put VDB, the limit will be VDB minus VSB, which is nothing but what? VDS. So, you will get an integration as minus mu into W square divided by, I can put the value of IDS in here, which is nothing but what? Mu into W divided by L into Cox dash into VGS minus VT into VDS minus VDS square by 2 into alpha. In the numerator, we do have an additional term of Cox square and this integration. So, this equation will be like this and this equation becomes 0 to VDS A minus alpha u whole square du. This will give you a closed form equation for Qi. So, let us move further with this. Again we will get Qi is equals to, if you see carefully, this mu and mu get cancelled, W and W get cancelled, one Cox will get cancelled and L will go in numerator. So, you will ended up with minus W into L into Cox dash, W into L into Cox dash divided by Vgs minus Vt into Vds. I am taking it out from the denominator. If you take it out, you will left with 1 minus Vds into alpha divided by 2 into Vgs minus Vt. So, you will left with 1 minus Vds divided by Vgs minus Vt into alpha divided by 2, right. Now, in the numerator, if you do the integration, this integration will give you, or let me rewrite again, 0 to Vds a minus alpha u whole square will give you a square plus alpha square u square minus 2 alpha u du, right. So, again I am rewriting this equation as this factor will come here. So, minus W into L into Cox dash Vgs minus Vt into Vds is common, 1 minus Vds into alpha divided by 2 times of Vgs minus Vt. Now, this will give you a square into du, right. Integration of du will give you u, when you put limit you will give you what, Vds plus alpha square u cube by 3 means Vds to the power 3 by 3 minus 2 alpha u into a. So, into 2a alpha, integration of u is what, u square by 2, it means what, Vds square by 2. So, this will be the final result, where a is nothing but what, Vgs minus Vt, right. Take Vgs minus Vt or a square Vds common. So, ultimately what will happen, in the numerator you will get W into L into Cox dash, you are taking a square, you are taking a square Vds common means Vgs minus Vt whole square into Vds you are taking it out. In denominator you will left with Vgs minus Vt into Vds in brackets 1 minus Vds into alpha divided by 2 times of Vgs minus Vt, and inside you will get 1 plus, here Vgs minus Vt square out. So, you will get alpha square Vds square divided by 3 into Vgs minus Vt whole square. Now, in the third term you will get 2 and 2 get cancelled, a is out. So, you left only 1 Vgs minus Vt in the denominator. Now, you have taken Vds out, so 1 Vds and alpha. Now, I know the formula for eta, which is nothing but what, 1 minus Vds divided by Vds dash. So, can I use this simple formula of eta to replace these complex equations in terms of eta? So, eta can be written as 1 minus Vds divided by, this can be replaced as Vgs minus Vt by alpha. So, ultimately you will get Vgs minus Vt into alpha. So, this quantity, wherever we are getting this quantity Vds into alpha divided by Vgs minus Vt, we can simply replace as 1 minus eta. So, let us replace, and first this will get cancelled, you will get minus W into L into Cox dash into Vgs minus Vt divided by 1 minus, what is this quantity? So, this quantity is nothing but 1 minus eta. So, you can write as 1 minus eta divided by 2. In the numerator 1 plus, what is this quantity? 1 minus eta whole square divided by 3, right, minus this quantity is what, 1 minus eta. When you solve for this, this will give you 2 minus and minus plus into eta. So, ultimately you will ended up, this 2 will go in numerator, ultimately you will ended up minus W into L into Cox dash, 2 will go in numerator, then this is 2 minus of 1 minus and minus plus, so it is 1 plus eta, and here you will get 3 plus 1 plus eta square minus 2 eta minus 3 minus and minus plus 3 eta divided by 3. So, this will give you in the numerator 1 plus eta square divided by 3, and this will go from this side 1 plus eta, and there is 2 in the numerator here. This 2 is went to numerator. So, you will get in 2, and hence after this calculation you will get a closed form equation for Qi in terms of eta, which is given by this, right. So, this will give you a closed form expression which we have calculated by replacing the variable from x to voltage. Similarly, by same example or by same approach you can calculate Qb. In the same example or same approach you can calculate Qg. The other way to calculate Qg is what? The charge balance equation, because we know Qg plus Qb plus Qi plus Q naught is equals to 0. So, if you are interested in Qg, ultimately you can simply write as Qg is equals to minus of Qb plus Qi minus of Q naught, right, where we have also already calculated Qb here and Qi here. So, when you put back you will get the closed form equation for Qg as this. Now, to calculate the fictitious charges which we defined as Qd and Qs, you need to do the integration, and by keeping x value, right, by L into Qi dash dV Cb. So, when you put x you need to again go back and use this value of x what we have derived here, right. So, when you solve this integration, ultimately you will get these equations which actually tells you what is the significance of this charge in terms of terminal voltages. So, to see closely, let us see two special cases. First special case, we are assuming what will happen if VDS is equals to 0. If VDS is equals to 0 means you are only applying the gate voltage, and throughout the channel the charges will be uniform, right. You are considering VDS is equals to 0. When VDS is equals to 0, what about eta? Eta is equals to 1 minus VDS divided by VDS dash, and hence eta will be 1. We can simply calculate by using previous equations. For example, let us consider for Qi dash only. When you put eta is equals to 0, you will left with Qi when VDS is equals to 0, meaning eta is equals to 1, sorry, not 0, VDS 0, eta is equals to 1. This will give you minus W into L into Cox dash into Vgs minus Vt, this quantity, into 2 by 3. If you put eta equals to 1, it is 1 plus 1 plus 1 divided by 1 plus 2. So, ultimately you will get 3 by 2. This will get cancelled, and ultimately you will get equation of inversion charge when VDS is equals to 0, which we have already derived when we were talking about DC analysis, right. So, this is showing a same resemblance with DC analysis, right. Now, however, in quasi-static analysis we are very much interested in the fictitious charges at the drain and the source side, how they behave, right. Then only we can decide what is the amount of charging current in respect to the terminal voltages. So, similarly, by putting eta is equals to 1 on the previously defined equations like this, you put eta is equals to 1, you will get some fraction. So, this is your inversion charge, this is your Qd, and this is your Qs. This graph shows how my charge varies with respect to VDS. For example, if your VDS is equals to 0, there is a gate charge, but when you increase the drain voltage, the gate charge will reduces towards the drain. Similarly, let us say this is your inversion charge. So, this is Qi, this is Qs, this is Qd and Qb. So, when you increase the drain voltage, what will happen? The inversion charge reduces. This is in negative axis, this will be much more than this value, right. So, here what happens is the inversion charge is reduces. you are taking a magnitude value, right, magnitude of charges. So, this is more charge as compared to this charge. So, when you increase the drain voltage, the charges is reduces towards the drain, which is obvious, because when you increase the drain voltage, ultimately the channel will go towards the pinch off. Now, let us see for the next case when we are considering what will happen when VDS will be VDS dash. So, exactly at VD equals to VDS dash, the eta will be 0. So, by putting eta is equals to 0 in our previously defined equation, you can calculate what is the bulk charge in saturation condition, inversion charge, drain 50s charge, source 50s charge, and gate charge. By doing so, you can simply relate how much difference the source charge and drain charge, which is 50s charge, is there. Why? Because when you are going towards the saturation, the drain charge or near the drain, the charges will be reduced. That is what, there will be a exact same charge near drain equals to 0, right, because you have a uniform channel if VDS is 0. However, if VDS is not 0, then the bulk charge here is increases and the inversion charge reduces. That is what, the reduction in inversion charge is can be supported by that QD is reduced then QS by this amount, correct. So, we can use this analogy or this expression to calculate the charges in terms of terminal voltages in strong inversion. Now, as we know, the modeling in the moderate inversion is really complex, because in moderate inversion we cannot simply start with the drift equation or diffusion equation. That is what we are going to do in weak inversion, whereas we need to consider both drift and diffusion simultaneously, and that is what we need to take utmost care when we are considering about moderate inversion models. So, let me summarize this lecture. In this lecture, we have discussed about the modeling of charge in terms of terminal voltages. We have just taken a DC analysis, but which is simply resembling the quasi-static analysis as QI. So, we showed that to relate the charge with respect to voltage, we need to change the variable, and we have changed the variable also as dx is equals to minus of mu into W divided by IDSN into dVCB into minus of QI dash, or it will be plus because I have taken minus out, right. So, how we can change the variable and how we can find out the total charge in respect to the terminal voltages. That is very important, because you remember the ultimate goal is to calculate the terminal current with respect to change in the charge with change in voltage, and we know the change in the voltage per change in time. So, if we can find out this, we can simply find out the terminal current. So, we will stop here for today. Until then, take care.